Thank you all for coming to this talk today. My name is Andrew Allman. I'm presenting on behalf of my advisor, Qi Zhang. This is work that we've done along with our undergrad, Qiu Li, at the University of Minnesota, and also in collaboration with Morano Martin at the University of Salamanca. In this work, we're going to discuss a supply chain optimization framework that we've developed that utilizes modular and mobile production units and showcases their benefit in biomass waste energy supply chain. To kick off this talk and motivate this work, it's important to discuss the prevalence of biomass waste. It turns out that for many crops that we grow a lot of, such as corn, soybeans, or wheat, greater than 50% of their biomass are inedible residues or waste. These are things such as stalks, husks, stems, leaves. They go by names such as corn stover, wheat straw, and alfalfa hay. It's a resource that we really have a lot of. In fact, it's projected that 155 million tons of these different residues are going to be generated in the United States annually by the year 2030. And so with the importance of sustainability, with this increased emphasis on circular economy principles, it's important that we're able to find a use for this highly prevalent resource. And so it first asks, what do we use it for now? And it turns out that the vast majority of this resource is going to be left in the field and potentially even burned. And while at first glance, it seems like this might be the lazy, low-cost solution of managing this, turns out that doing so does have some benefits. It can help prevent soil erosion and replenish nutrients to ensure that the farm is profitable in future years. In comparison, a much smaller amount is also used for the care of farm animals, for things such as animal feed or animal bedding. Nonetheless, it's estimated that at least 40% is not going to be needed for any of these purposes. So we can ask ourselves, what can we do with this? For example, can it be useful to use this biomass waste to be able to generate energy? And the answer to this question, at least in theory, is yes. There are many different technologies that exist that can convert biomass waste to energy. One of the most promising technologies is this gasification process shown here. At a high level, what we're doing is we're taking biomass such as corn stover, passing it through a gasifier to produce syngas, and then expanding that hot syngas in a turbine to generate electricity. Nonetheless, as I'm sure you're all probably aware, this is not a technology that's that widespread in its use, so clearly there are some challenges with regards to its implementation. What are these challenges? So one of the most critical challenges is the low density of biomass waste. For example, if I were to go to different farms and collect all of those biomass waste and put in a truck and send to a processing facility, inside one truck, I can fit about 1 ton of biomass. If you remember, we're talking about a resource that we have tens of millions of tons of. So clearly, we need lots of trucks to get our biomass from point A to point B. So it's going to be very expensive. Make the transportation costs a little less expensive, but that requires investing capital in drying or compacting. So clearly, transporting biomass waste is an expensive challenge, one that is exacerbated by the fact that biomass waste is also a distributed resource. So if we look at this heat map in Minnesota here, that shows that biomass waste comes from pretty much everywhere. And we not only have the expensive truck transportation, but now we have to get trucks to every corner of the state of Minnesota. And then this profile is going to be similar when we look at the United States as a whole. And this is not, we look at this map, this is just one snapshot of the distribution of biomass waste production. It's also this production is also distributed in time, such that if we were to look at a different year or a different month, this heat map's going to look a little different because different crops are being produced at that time. And so, what's our answer to this high transportation cost is, well, let's not worry so much about transporting the biomass waste. Let's instead worry about transporting the processing equipment and bringing it directly to the biomass. And so that's the idea behind using modular and mobile manufacturing. I'll just give a brief overview of what we mean by this. We mean units that can be constructed off-site, then stuck on the back of a truck, sent to a processing facility, and assembled with other units, almost like Legos, into a working facility. If the supply dictates at a later time, we can disassemble these facilities and transport the modules again on the back of a truck to a new location. Different modules can have different sizes. That gives us different options of how we want to process a fixed amount of biomass. And importantly, for this particular application, different modules can have different functionalities. In particular, our biomass waste to energy is going to have two different functionalities. Again, we're going to have that gasifier that converts the biomass waste to syngas, as well as a turbine that expands that syngas and generates electricity. So our goal then is to develop a supply chain optimization framework that decides how to build and relocate these modular and mobile biomass waste energy units on processing all of the biomass that's supplied to us at a minimum cost. And so we're going to briefly go over the equations here. I just want to point out that this comes from this adapted from a recent publication that we've published for modular and mobile supply chains. That focuses more on the solution methods, on different computational studies. So if you're interested in that, I encourage you to go look at this paper. In this particular talk, we're going to focus more on the specific application of biomass waste energy. And so our objective value here is minimizing the sum of operating costs, cost of relocating modules, and capital costs of building modules. And our objective is subject to the constraints that we need to process the entire amount of biomass supplied to us. We can only process as much biomass as we have the available capacity for. We use a conservation equation to keep track of the number of units built at different locations at different times, and only allow operating configurations that conform to the amount of units we have. And lastly, we only allow each location and each time point one configuration. So before we get into the specific biomass waste energy case studies, I briefly want to go over a few key concepts. Again, these come from our previous paper. First is this idea of configurations. These are, for this particular example, this is going to be different allowable combinations of gasifiers and turbines that form a working facility. We also have this idea of the supply center of mass. This is basically a supply weighted average location. It tells us where on average our biomass is coming from. And lastly, we have this value of module mobility, which tells us the benefits that we're incurring from allowing modules to move from site to site versus fixing them at the location we build them at. And a key conclusion that we came to in our previous work that we'll see again for this particular example is that movement in our supply center of mass over time is going to be a driving force for high values of module mobility. So what I want to do next is go over two different case studies that we're going to look at in this work. So we look at processing biomass waste from two different states, Minnesota and North Carolina. How are they different? North Carolina has a longer growing season, 8 months instead of 4. They have differing number of counties, which we consider as the locations where our biomass waste is coming from. Differing number of production sites, which we assume to be located close to population centers within the state. They grow slightly different crops. Both crops grow soybean, wheat, and corn. North Carolina also grows some alfalfa hay. In order to keep the comparison roughly apples to apples, we try to keep the average amount of biomass waste that we need to process per month the same. And so to do that, we only process a certain amount per month. In North Carolina, it's 20% of its actual residue produced. In Minnesota, that's 1%. So based on that, it's clear that Minnesota is producing a lot more biomass waste per month than does North Carolina. We also consider differing unit capacities, both small and large gasifiers and turbines. Small units are mobile and completely flexible in operation. Large units are immobile and can only be scaled down a certain amount. If we consider all possible combinations of small and large gasifiers and turbines, that gives us 24 allowable configurations. This slide shows the results of one case study looking at processing biomass in Minnesota in the year 2017. Here we show the results of the optimization, the different color squares superimposed on heat maps of biomass residue production. Here we have different squares for gasifiers and turbines. We have open squares when they are not in use, closed squares when they are actually processing biomass. We can see that they move throughout the state between the different months as the supply center of mass moves from the northwest part of the state down to the south central part of the state. We also looked at processing the biomass from a different year. So this is 2018. What you may be able to tell here is in this case study, there's a lot more biomass present in the earlier months of August, September, and October, less in November, a later month. And so what actually ends up happening here is we build one less large unit, so only 2 large gasifiers and turbines instead of 3, because we only need them for 1 month. In contrast, we have a few more of the small units, and we take advantage of this flexibility and this extra movement in the supply center of mass to move the different units around from location to location over the 4 months. We also look at this case study for North Carolina in 2017. So again, just a different location that has a longer growing period that uses different crops. And here we can see a lot of the same things happening. Now we're moving our biomass production, our biomass processing units to different locations throughout the state as the production profile changes from month to month. Again, this was an 8-month simulation, so we also have the last 4 months shown here. The results of these 3 different case studies, the numerical results are shown on the slide. So here what we see, again, we have about the same, roughly the same numbers of modules being built in all 3 case studies. We see that the North Carolina case study has an annualized cost of about double the 2 Minnesota case studies. This is mainly because, again, we're operating over 8 months instead of 4, so we're processing. So we need to transport 8 months worth of biomass instead of 4. Nonetheless, for the North Carolina case study, the average cost of electricity is less because, again, we're processing more total biomass over 8 months, even though the per month biomass is about the same. Our values of module mobility range between 1% to 4%. And again, this accounts for millions of dollars a year, as we can tell from the annualized cost values. What you might be asking yourself now is, you showed me these differences between optimal supply chain for the same state in 2 different years, but we're probably going to need to decide what modules to purchase before we know if the biomass production is going to look like, for an example, a 2017 or 2018. And you'd be exactly right in thinking this. And so what we did is we developed the two-stage stochastic programming framework that accommodates this reality, where we're considering our module purchases as a first stage decision where we have to make before we know what the biomass production profile looks like. And we have some wait and see decisions that refer to our biomass processing and module movement. These manifest itself in the objective and these operating costs, which now have an expected value because different scenarios in biomass production can play out. We manage this by taking a sample average approximation to replace the expected value with an average, and then we give equal weight to multiple years of historical data. So we show some results of running the stochastic program here. This slide shows the value of running a stochastic solution. So on the left, we have the results of the two-stage stochastic program. On the right, we have the results if we determine how many units to build and where to build them based on an expected biomass supplied. And by looking at these columns, we can see that the real benefit of stochastic solution is that we can avoid infeasible decisions. We can avoid decisions in which modules to build that are going to be infeasible for different years. On this slide, what we're showing is results of the stochastic solution compared to the minimum, maximum, and average results of 5 different deterministic solutions using the demand profiles for each of these 5 years that we considered. And what we're seeing here is that we're building slightly more modules than the average what we do on average in the 5 years. We also have slightly higher costs than we do on average. Again, this is not an unexpected result. This is just the cost of managing the uncertainty. The most important and interesting result here is that our value of module mobility in the stochastic case is higher than it is in any of the deterministic cases. This is actually a result that we expected because if you're looking at building units at a fixed location over 5 years, then you're going to have more years and more months where you're stuck with units in a location where it's going to be expensive to transport biomass to and operate them. So this is an expected result. It shows that being able to move units provides an additional recourse action to hedge against our uncertainty. So just to briefly conclude our talk, what we showed today is that modular and mobile production units can be beneficial in saving money in biomass waste energy supply chains. We've built a generic framework that's useful for different locations, different crop profiles, and we've shown that mobility is even more beneficial in a stochastic case as it provides a means to hedge against uncertainty. In the future, we're going to extend our work by considering a multi-stage stochastic program for a multi-year plan. I want to finish by thanking the support of my fellow group mates at the University of Minnesota. I'll be happy to answer any questions that you have.